Okay, then also good afternoon from Toshiba side. My name is Rainer Kaese. I'm doing the business development for the enterprise hard disk drives in Toshiba, and I'm happy to join Starline for this seminar as the hard disk drive partner, as one of the hard disk drive partners of Starline. As I said, we are a hard disk drive vendor, and kind of how we come to contribute to this Ceph storage webinar series is because of we are supporting the industry. We are also supporting Starline with hard disk drives. We are running an application lab here in Düsseldorf in Germany, our headquarter, where we also exercise our hard disk drive in large storage systems, also doing proof of concept activities. And what we have done together with Starline in the technology experience lab of eShelter, now NTT, we have several large storage setups. For example, in the Frankfurt lab, we have a ZFS system. And together with Starline, we have built up a Ceph cluster in the Munich innovation lab of NTT, where people can exercise Ceph-based storage. Out of this activity, the Starline guys have asked me to contribute to this webinar from hard disk drive point of view. In the first session, I have been discussing about when to use hard disk drives, when to use SSDs. And I gave a little bit of background of kind of when we can use cheap and when better go for quality and what are the differences. For this session, I would like to touch two questions. The often asked question, should I use SAS drives or SATA drives? And the often asked question, why should I use Toshiba drives? So if it is SAS and SATA, just to recap, SATA is an interface coming from the client side. It's a rather simple interface, just a single channel, 6 gigabit per second, rather low voltage swing because it's meant for short cables from motherboard to CD-ROMs to hard disk drives. Due to coming from the client side, usually the volumes manufactured with SATA interface are rather large. SAS, however, serial touch SCSI, is a more complex interface. It's a kind of genuine enterprise interface. It has two channels, can go up to 12 gigabit per second with a higher swing. It has an end-to-end protection. Compared to SATA, the volume of manufactured drives with SAS interface is lower, typically 1/4. Some other things to state before going into a discussion. Large infrastructure, like kind of all the infrastructure for storage systems, host bus adapter cables, the expanders, the backplanes, is nowadays always SAS 12 gig based. So all the cables, all the interconnect is SAS 12 gig. However, this is backward compatible to SATA. So you can insert SATA drives, it will work. You can also insert SAS drives, it will work as well. The other thing which we should be aware of is that this SATA 6 gigabit per second interface is fast enough for any hard disk drive. So from performance point of view, there is no meaning or no advantage of going to the SAS 12 gig. So the 6 gig of the SATA giving us 600 megabyte per second as a maximum speed roughly, and the fastest hard disk drives are around 250 megabyte per second. Our new series is almost 300 megabyte per second, but that's still half what a SATA, the slow SATA interface can take. The enterprise capacity, or sometimes called nearline hard disk drives that are used for the larger storages, they are available with a SAS or SATA interface, optionally. So there's no other difference. The lineup of SAS drives and SATA drives is the same. Also the quality, the mean time to failure or the annualized failure rate or kind of the general durability of the drives is the same. Also, the speed is the same. It's just that the interface is different. So in previous times, it was often considered as SAS is more high quality interface for enterprise, while SATA is a low quality interface for client. If you're talking about the enterprise capacity on nearline drives, that's not true anymore. SATA drives are as reliable as SAS drives. Only due to the complexity of the SAS interface, they have a slight cost premium, about $10. And what's also important to know is that SATA drive fit into a SAS infrastructure, but not vice versa. A SAS drive you cannot put into a SATA infrastructure. Now, given that, we can give some advices for best practice when to choose SAS and when to choose SATA. So obviously, if you have a single hard disk drive on a motherboard, SATA is probably the choice to go because on all the motherboards, there are SATA interfaces. If it's a single SSD on a motherboard, like the typical boot device, SATA can be used, or in newer systems, NVMe, PCI Express. If your system need to be spec'd for high availability, so no single point of failure, SAS drives with their two interfaces can be connected on two redundant paths to different hosts. So for high availability, SAS is mandatory. So that's pretty clear. Where basically both options are available is for larger infrastructures. So if you have SAS cable, SAS expander, active backplanes, and so on, then SATA hard disk drives will still work. From the SATA, kind of the simple SATA interface, from the hard disk drive to the first expander, it's not a very long way because the backplane is active, you don't have long paths. So on this short distance to the first expander, the SATA interface will work. Putting a SAS drive in such a large infrastructure will give no real advantage. There is a minor advantage if it is if the 12 gigabit per second from the SAS drive can fill the relatively small buffer of the hard disk drive, can fill it faster than with the 6 gig SATA interface. But this is only if it is a kind of very much IOPS driven storage. It gives you a few IOPS more with SAS interfaces. But if you're talking about large infrastructures, like dozens, hundreds of terabytes up to petabytes, IOPS of hard disk drive is anyway not the issue. If you need IOPS, you better do kind of caching, journaling, tiered storage with SSDs. Out of our experience, there is one situation where SAS hard disk drives are definitely preferred. If it is a smaller infrastructure, namely the passive backplanes, because the low single swing of the SATA can cause problems on long backplane connections. Because SATA was designed for kind of short connections, motherboard to drive. So these passive backplanes of 12, 16 drives, 24, sometimes 24 drives, in the typical front-loading server or the Supermicro with front and back connections. Here, the SAS, due to the better signal quality, is definitely preferred. And these two advisors, like SATA for the large scale up, scale out storages, SAS for the smaller enterprise server, we can see also in the market. For enterprise server, people are using SAS for that reasons. All the hyperscaler, all the big scale out storages using mainly SATA drives for the same reasons or argument explained. finally, the guys in Starline know exactly about this, and they will definitely choose the right selection for your storage. Okay, and the final question: why Toshiba? Why Toshiba hard disk drives? Well, you as Starline customers definitely benefit from the good partnership and the close connections between Starline and Toshiba. So, as I said earlier, Starline will select the best suited hard disk drives for you. Starline has very early access to all our new hard disk drives from the lab. So even with sniff samples out of the development, so they are testing, they are qualifying our hard disk drives. We have direct open communication. So if there is any firmware update, if there is sometimes a reason for to do the troubleshooting, proof of concept activities, we are in very close contact with Starline. Starline always has access to us to the kind of newest firmware right away, to the newest hard disk drives right away, and you can benefit from this partnership by getting the latest technology best supported. Just a few words about the enterprise capacity lineup of Toshiba. I said earlier, they are coming with SAS and SATA interface. So the lineup of the SAS drives here and the SATA is almost the same. Only in the SATA, we still have a 1 terabyte for kind of legacy applications. The major lineup goes from 2 to 18 terabyte. Up to 10 terabyte in Toshiba. We are manufacturing the drives with airfill from 12 to now 18 terabyte. The drives are filled with helium because we want to fit more thinner platter, and in air, the thinner platter would flatter. In helium, which is a very light homogeneous gas, they run more stable. All these drives have conventional magnetic recording. So no shingled magnetic recording, which may cause compatibility problems. The 18 terabyte, which was recently introduced, is the current top model, and it's the world's first model with microwave-assisted magnetic recording. So that's a type of CMR, so it has the same features and the same performance, same behavior as the conventional recording. Just we have added a microwave generator to focus the magnetic field, to have a more strong magnetic field in order to flip smaller areas. The drives are available in the 512 emulated block size, 4K native. We also have options for self-encrypting drives and for drives with this nice sanitize instant erase feature, where you can wipe a drive instantaneously. Very important for if you don't have the time for overwriting it when repurposing the server or storage. A few comments about the technology. The 14 terabyte 3.5 inch drive was introduced in 2018 with the helium technology I already mentioned. With the helium seal, we can do 9 disks, giving us 14 terabyte. In 2019, we added a very small technology add-on called two-dimensional magnetic recording, which simply means instead of one read head, we now have 2 read heads with a slight mechanical offset, so that the read head can have a difference in the fringe noise from the adjacent tracks. With some equalization, in a digital signal processor, we can distinguish between coming from the right track, coming from the left neighboring track, that giving us higher signal noise ratio, allowing us to make the magnetic bit smaller and fit 16 terabyte in the same space as the 14 terabyte. Earlier this year, we introduced the 18 terabyte on the same 9 disk TDMR structure. Here we put the already mentioned microwave oven to have more magnetic energy, means we can make the write head a little bit smaller, fitting 18 terabyte on the same 9 disks. There is the shingle magnetic recording technology available as well, and we will soon have a 20 terabyte on the same technology, just with slightly overlapped written tracks. But this hard disk drive is only suitable for large archives, and as it is a host managed device, also the appropriate management system in the host have to be in place to use this 20 terabyte, and it's only for sequential data. So we don't expect that this will have a major usage in multi-purpose server and storages. Nevertheless, for large cloud backup archive storages, people can get 20 terabyte for the price of 18 with the demerit of the lower performance. So this is where we are today, 18 terabyte. Two more things for the future of the mechanical hard disk drives. At the moment, we are at 9 disks. If you can fit 9 disks, you can also fit 10 disks. So we have a mechanical demonstrator that rotates 10 disks. It works. It is not yet clear in which generation we will introduce the 10 disk, because the nice thing about the 9 disk, since we have it for 3 generations, it's the same mechanical platform, it's the same components, it's the same thickness. So from a manufacturing point of view, that's very attractive. The 10 disk will initially be more expensive, but the aim of the industry and also of Toshiba is not to make hard disk drives significantly more expensive, but more or less stay with the same price, just add capacity. If you would offer a way more expensive hard disk drive just with 2 or 4 terabyte more, it would be easier to buy 2 of the older ones for a cheaper price. So the optimization criteria for the hard disk drive nowadays is not what is technically feasible. Technically feasible is a lot. We even have proven that 50 to 100 terabyte is technically feasible within 5 to 10 years. Yeah, the question is, can we manufacture it for the price that keeps hard disk drives as the lowest and most attractive storage media from price capacity point of view? If you need a 10 disk, we will introduce it when it's cheap enough. One more future outlook is what we call the multi-actuator. Well, the problem with the hard disk drive, we have 18 to 20 terabyte. We will have 24 terabyte and even more. And it can be filled only with 200 to 300 megabyte per second because we have only one interface. We have only one arm moving over the magnetic surface. Filling the hard disk drive with data takes weeks. And the rebuild, if a hard disk drive fails, would take weeks as well. So there is an approach, or there is a need for making hard disk drives faster. We will never have them as fast as SSDs. It's just due to mechanics. Yeah, it's still a mechanical device. But we would like to have them at least a little bit faster than they are today. And one approach, well, the initial approach was, or the initial idea was to have 2 arms. One arm here, one arm there, but that wouldn't fit into the mechanical housing. What fits is if we split the arm into 2 actuators that run independently. In this way, we basically have 2 interfaces. We have twice the interface speed and twice the IOPS for the hard disk drive. So also this is a prototype that it's existing. We could manufacture it right now, but here also kind of for the same reasons explained earlier, there are still 2 things which are a little bit of an obstacle. One is on the split level, we lose one platter. So for the same manufacturing cost or for the same price, it will have at least 2 terabyte less. And we have not yet finally confirmed whether people want to pay more for capacity just to enjoy the faster speed. The other thing is At the moment, it's not yet clear on our large and lead customer side whether we should do this with a SAS interface, where we basically have two LUNs. So the two channels of the SAS interface, both one take 9 terabyte, the other one take the other 9 terabyte. Or there's another big customer who's more on the SATA side. So he want to have basically a SATA interface, one SATA interface with one LUN at about 500 megabyte per second. I guess in the end, we and also the industry may do both, but it's not yet determined how exactly this will be implemented. And that's it from my side. I would say thank you for listening, and back to Starline.
So thank you, Rainer, for your presentation. And I will now hand over to Amar with the next presentation.
Thank you, Konrad. Hello, everyone. Also, thank you to Maged and Rainer for joining us in this webinar series. In this episode, we will discuss the important points you should consider when choosing your hardware for a PetaSAN erasure-coded Ceph cluster. We will be using a detailed real-life example. Let's first do a quick recap on what we discussed earlier. We talked about the 5 core software components of Ceph, the monitor, which is responsible for monitoring stability and client cluster authentication. We said we need at least 3 of those within any Ceph cluster. The OSD, which is responsible for data storage. You need as many of those as you could to guarantee good throughput and data resilience. The manager provides additional monitoring services and can interface with external monitoring and management systems. It runs parallel to the monitor. The metadata server stores metadata on behalf of the Ceph file system, and you only need it if you plan on using Ceph file system. The gateway, which acts as a bridge between the cluster and the clients, and you only need a gateway if your clients cannot directly connect to the cluster using Librados. Basically, you need a gateway if your clients are going to connect over a common access protocol such as an iSCSI, NFS, or an SMB gateway. Linux clients with the modern kernels do not actually need a gateway. They can directly connect to the cluster. We also talked about Ceph as a redundant clustered storage system where all members of the cluster are networked, actively interacting, and always aware of each other's status and function. All those members can use and benefit from the Crush algorithm. It's the smart algorithm that powers Ceph. We said that within Crush, you can also define your failure domains. Your failure domains are basically the components of your cluster that you can afford to lose without interrupting service. We discussed the 2 main mechanisms that Ceph uses to store data, replication and erasure coding. Replication is very simple. You take an object, you duplicate it an X number of times. The default value for Ceph is 3 copies for each object, which can make replication somewhat expensive disk space-wise. We also highlighted how erasure coding works. We said that erasure coding takes one object, splits it into a number of data chunks, then calculates and adds a number of encoding chunks. Then all those pieces get stored into different OSDs based on your erasure coding profile. This means erasure coding is a calculation process. It requires some processing, and when building erasure coding clusters, it's very important to take note of this computational overhead. We also highlighted that in the event of an OSD failure, Ceph will have to retrieve all the surviving data chunks and encoding chunks from the active OSDs. Then the erasure coding engine will use those chunks to rebuild the complete object. The recovered object will then get written back to the cluster. We said that an erasure coding profile of 3 plus 2 means the ability to lose up to 2 OSDs or OSD nodes. An erasure coding profile of 6 plus 3 in contrast would mean the ability to lose up to 3 OSD or OSD nodes. So the M here defines your OSD failure tolerance. When using erasure coding, it's recommended to set the M to a value of 2 or more to prevent loss of data, and erasure coding setup of K plus 1 is highly discouraged because in the event of one OSD or one node failure, you can lose some data. Also, your pool will be read-only until the object has been recovered. So, 2 storage mechanisms to choose from. Replication is more space consuming but relatively more performant, especially for a smaller number of nodes. Erasure coding, which is more space efficient but on the other hand is more CPU and RAM hungry. It also has a relatively slower write speed, especially for small scale clusters. We said that everything within Ceph is software and that we need to pay attention to the recommended CPU, RAM, disk, and network resources those software components require to happily operate. We also said that there is some homework one needs to do before settling for a hardware configuration. We need to define the use case, we need to narrow down the actual throughput and IOPS requirements. We need to be somewhat exact about the failure tolerances. We need to check our existing networking infrastructure. Anything slower than 10 gigabit must be discarded. Finally, we talked about Starline's recommendations for our PetaSAN Ceph solutions, and we quickly compared them to the generic recommendations available from different sources. We said that our rule of thumb is to use a 1-to-1 CPU cores to OSD ratio. This means that in a 12-base chassis, we would use a 12-cores CPU. If the chassis is going to run any critical services such as an iSCSI or an FS or SMB gateway, then I would add at least 4 more cores to the mix. The above rule goes hand in hand with the rule that you must have sufficient RAM for each OSD. We use a minimum of 5 gigabyte of RAM per OSD for HDD-based clusters. That being said, and when I/O performance is not your top priority, such as in the case of archival and cold storage clusters, you can count a virtual core towards the total number of cores. So for a cold storage cluster, I would be using an 8-core CPU with hyperthreading that gives me 8 actual cores plus 8 virtual cores and a 12-base chassis. But the RAM would never go below 5 gigabytes per OSD. Here is our real-life example and today's exercise. Let's try to configure a PetaSAN erasure-coded cluster based on this customer's requirements. The customer says, I need 2 petabytes of usable capacity, expandable to 3 petabytes within 2 years. I have 3 data center aisles, 4 4U rack spaces available within each aisle, 10 gigabit networking available. The cluster is going to be for backup. He will be using iSCSI. He expects between 1.5K steady IOPS and 2K peak IOPS. He might need some more performance from the cluster in the future. He's not sure about it. He doesn't know Ceph, but he knows that it's cool. He has a limited budget. So let's start with the basics. We need 2 petabytes usable, and it's very important here to take into consideration the near full limit and the full limit of Ceph. At 80% usage, your cluster will start sending you warnings that it's getting full. It's wise at that point, even before you hit that point, that you start adding OSD nodes to your cluster, or at least start replacing OSD disks with bigger ones if you have no chance to add OSD nodes to the cluster. If you keep ignoring the warnings and continue to fill your cluster, once you hit 90% full, the cluster is going to go into read-only mode. Your clients will not be able to write data to the cluster. If you're using your cluster for live VM images, all the connected VMs will simply crash. You are now in a dire situation that will cost you more in support charges than it would have cost you to just add a couple more OSD nodes. Next, we try to understand the different technical and logistical limitations. This can help us optimize the configuration and compose a proper solution for our customer. From the given information, we have room for up to 12 4U chassis. This is good because we can use high density chassis to save some rack space and some costs. We need to find the balanced number of nodes for the desired capacity, the expected throughput, and the existing 10 gigabit networking. We should also make use of the available aisles and try to spread the cluster within the data center. By spreading the nodes over as many racks and aisles as possible, we can have a better level of protection against service interruption within one or more rack or aisle. The next two pieces of information, the build is going to be for backup, and they have a limited budget. Because of the budget factor, we need to use a fewer number of chassis with a relatively higher number of disk drives per chassis. So we went for a 36 bay chassis here. Those are dense enough, and looking at the amount of available rack space within the data center, we can fit up to 12 of those chassis in there. We also knew from the customer that they will be using tape backup for the cluster. So there is long-term backup for the backup cluster, which is excellent. The trick here for the node count is that you want to achieve a few things. You want to spread the cluster over as many racks and aisles as possible. You want to leave some rack space for future expansion or emergency recovery, where you would have to plug in a node or two to replace some failing nodes. You want to use a reasonable OSD disk capacity, individual disk capacity, because the higher the individual disk capacity, the longer the recovery time is going to be for each OSD you lose. This means a 4 terabytes OSD disk loss will take the cluster less time, basically half the time, to rebuild than an 8 terabyte OSD disk. Usually we dedicate nodes for monitors, but because of the customer's use case, which requires relatively low IOPS, we can take advantage of one brilliant feature in PetaSAN. We will be combining storage and monitoring functions on 3 of our chassis. This means we do not have to spend money on dedicated monitor nodes. This also means we can save some valuable rack space for future expansions. To combine monitoring and OSD function on your nodes, all you have to do when installing PetaSAN is to tick both management and local storage boxes during the initial PetaSAN installation, and you're set. With monitor and OSD services combined on 3 chassis, we can save 3 out of the total 12 slots, and our total number of nodes would be 9. 3 nodes doing monitoring and OSD function, storage function, and the remaining 6 will do pure OSD work. The next step would be to define the required single disk capacity, but for that we need to decide one important thing first. Which erasure coding profile are we going to use within those 9 nodes? When you have 9 nodes, you can choose between different EC profiles, such as 5+4 or 6+3, 7+2, etc. So which one is it going to be here? Let me give you the answer first, then we go over the why as we speak. For this build, we decided that we're going to go with 7+2 erasure coding profile. This means that we can enjoy the equivalent capacity of 7 nodes for our data and 2 nodes for redundancy. This also means that the cluster can sustain the loss of up to 2 nodes without going down or interrupting IOs. Now that we know we will use erasure coding 7+2, how do we fit 7 petabytes worth of disks into 7 nodes? Easy. Node capacity equals the required capacity divided by the number of data nodes. So the required capacity is 2000 divided by 7 nodes gives you about 286. 286 divided by 36, which is the number of slots per chassis, gives you about 8. So we should use 8 terabyte disks in each of our 36 bay nodes. Correct? Wrong. Why? Because we did not account for the 80% near full ratio. Remember slide number 11. If we use 8 terabyte disks, we will end up with a gross capacity of close to 2 petabytes. But then the usable capacity, the actual usable capacity, would be far less than 2 petabytes. Also, it's not 2000, it's 2048. It's a minor difference, but it can slightly affect the overall result. So we must have a gross capacity of more than 2 petabytes to end up with a usable capacity of 2 petabytes. So let's try again. 2048 divided by 7 gives us approximately 293. 293 divided by 36, the number of bays, gives you 8.1. Now we take this 8.1 and we multiply it by 1.24. The 1.24 is the factor that we use to compensate for the 80% near full limit of Ceph. Now you can see that we should be using 10 terabyte disks. So let's run a quick sanity check here. It's 7 multiplied by 36 by 10 multiplied by 0.8, which is the near full limit, divided by 1024 gives you 1.97 petabyte. This is as close as we could get to 2 petabytes without wasting space. Now that we have found a proper individual disk capacity, let's go back and reflect on why we chose the erasure coding 7+2 profile. Why didn't we choose something like 9+3 or 8+2 or whatever combinations possible? Why not utilize all 12 4U slots within the data center? Why not 12 terabyte disks, for instance, or even denser nodes? Okay, here are the things that we knew. In addition to the starting usable capacity, the customer said he wants to be able to grow to 3 petabytes in the future. This means if we eat up all 12 server slots, there will be no more empty rack slots, and we would be forcing the customer to add more racks or possibly moving walls to increase the total capacity of his data center. A 7+2 configuration would leave room for 3 more 4U units for future expansion. Also, we knew that this cluster is for backup. It's going to be filling at a relatively slow rate of approximately 1 petabyte per year. He has 2 years ahead of him before he would need more space. So it's a relatively reasonable IOPS demand here, and because he won't fill it anytime soon, there is no need to go for 12 terabyte disks. At a price difference of 40 euros per disk, the customer would end up paying about 13,000 euros more for free space that he would not use for about 2 years. We also knew that they will have tape backup for the cluster. We always use enterprise disks with high MTBF rating. We never use desktop grade disks. We don't even have them in store. And we also do burn-in tests before shipping out. But it's always good to have some sort of a safety net regardless of the technological and logistical assurances. We also know one important thing about Ceph and erasure coding. If you have 10 gigabit networking and you have to choose between erasure coding of 8+2 and erasure coding of 7+2, because of the nature of erasure coding, the higher the number of the nodes, the more bandwidth that will be consumed for read and write operations. So 7+2 will tax your 10 gigabit network less than the 8+2. So if you have to choose between 8+2 and 7+2 with a relatively moderate throughput network like the 10 gigabit compared to what we have in the market right now, go for the 7+2. It's also smart to always leave some space in the racks just in case of a single node failure where you would have to plug in a node for recovery or for a monitor replacement or something like that, so you don't have to lay your equipment on the ground. So the final answer here is that when building a storage solution, you are trying to find the sweet spot, a balance of things based on what you know about your customer and what you understand of the technologies involved. Since we mentioned MTBF here, I would like to refer you to an excellent article on Toshiba's website. It's titled What Hard Drive Reliability Really Means, and it's written by no other than Rainer himself. It's a very informative article and it clears a lot of confusion about the real meaning of disk reliability. There is also a relatively short 4 minutes video by Rainer about the calculations of the MTBF. And if you would like to read it or watch the video, I will give you the links at the end of this presentation. So the argument, someone might argue here, yes, but you said before that you can replace OSDs with bigger ones to increase the total capacity. You also said that the higher the number of the nodes, the better the overall reliability and throughput of the cluster would be. So why not just use all 12 rack slots and when the time comes, replace the OSDs with bigger ones? Both statements or arguments are correct, but replacing individual OSDs is very time consuming. And you are technically forcing the cluster into recovery by inducing an OSD down situation. You have to down the OSD, eject the OSD, and replace the hard drive. You also have to do this one OSD at a time, and you have to wait for the cluster to recover the data. So it's smarter and overall more efficient to just add more chassis to your cluster than to drop OSDs one by one like a serial killer. On the other hand, using a fewer number of nodes with a higher number of disks per node means that in the event of a node failure, a bigger portion of the data is lost. Imagine if we used 5 nodes, 72 bays each, in a 3+2 EC setup, that's 5 nodes. If one node goes down, you just lost 1/5 of your cluster. While in a 7+2 setup, you would lose 1/9 of your cluster. Less data lost means less data to recover, which translates to a shorter overall recovery time. So it's better to use 7+2 rather than 3+2 when you have the space and resources for it. Combining all the information we had, the different level of redundancy and protection, the tape backup that the customer will be using, plus the reliability of the supplied hardware, the reliability of the disks themselves, the inherent resilience of Ceph, plus the support you receive from PetaSAN and Starline, and EC 7+2 is sufficient to say the least. Now that we have an erasure coding profile and a node count, let's move on to individual node configuration. We have a couple more pieces of information that can help us decide which components to choose. The customer said he's going to be using iSCSI. The client machines are not Linux, so there has to be a gateway. Here we will benefit from another smart feature in PetaSAN, and we will run the iSCSI gateway service on 2 of our 9 nodes. 2 allows for high availability, and if there is an issue with one of the gateways, the I/O operations to the clients will not be interrupted. In this case, we decided to run the gateway function on 2 of the MON nodes. Those nodes will get the more powerful CPU. If you look at the configuration here, we have basically the same configuration for both the hybrid nodes and the pure OSD nodes. The only difference that you would notice here is the CPU that we have used. For the hybrid nodes that are going to run storage services, monitoring services, and act as gateways, we chose a 64-bit CPU at a base frequency of 2.8 GHz, but with 24 cores. The amount of RAM, the number of 10 gigabit interfaces, and the hard drives for the operating system, for the PetaSAN operating system, are basically similar. Why the difference between the CPUs here? We said in the previous session that when I/O performance is not a top priority, such in the case of archival and cold storage clusters, you can count a virtual core towards the total number of cores. And this is what we did here. We use a 16-core CPU for the 6 OSD-only nodes. I know that even with the hyper-threading, the total number of cores, actual plus virtual, is 32, which is like -4 cores lower than the number of disks. But this is a hard disk-based cluster. The CPU will always be able to catch up with the OSDs. For the RAM, we fit all nodes with 256 gigabytes of RAM instead of 192 for the pure OSD nodes. Why? Because the customer indicated during the initial conversations that he might want more performance out of his cluster in the future. So to allow this customer to enjoy the current required performance levels and at the same time give him the ability to up the performance with the lowest possible financial and logistical overhead, we equipped all the nodes in the cluster with dual CPU capable mainboards. We populate the main board with a single CPU, but you have the chance to add one more CPU in the future. Now when the time comes for an upgrade, all the customer needs to do is just plug in one more CPU and add some more RAM, and he's done. We highlighted this in the previous session when we said that it's best to add some hardware padding for future upgrades. This is why we gave the pure OSD nodes the same amount of RAM and basically identical configuration. As for activating iSCSI on the chosen nodes, simply check the iSCSI box during PetaSAN's initial installation. This can also be activated post-installation from within PetaSAN's GUI. All you have to do is just go to the nodes and click on the node that you wish to activate iSCSI on. Just take the iSCSI box and that's it. Here's our final hardware configuration. As you can see, we will have a total of 9 nodes. 3 nodes are going to be running OSD service, monitoring service, and gateway service. The rest are going to be pure OSD nodes. All the nodes are going to be doing storage in this scenario. The hybrid nodes will have a 24-core CPU at a base frequency of 2.8, dual CPU capable mainboard, 256 gigabytes of RAM, 2 SSDs for PetaSAN operating system in RAID 1 configuration mirrored. You need one hardware RAID adapter for the operating system disk. This is because PetaSAN does not support software RAID. You have to use a RAID adapter just for the operating system disks. We opted for the Toshiba MG0 series here. We offered the customer a choice between the SATA and the SAS variants at 10 terabyte capacity. We need one SAS adapter for the OSD disks, and we would plug in 2 dual port 10 gigabit network interfaces. This means each node would have a total of 6 10 gigabit network interfaces because the main board comes with 2 10 gigabit network interfaces on board. Finally, here are the links to Rainer's article in QR format. This again was a very basic walkthrough for how to select and configure a PetaSAN Ceph cluster for Asia coding profile. I hope this was informative, and if you have any further questions, please feel free to contact me through email, and thank you for listening.
Thank you, Amar, for your presentation. And I will directly forward the moderator to Maged. If you have any questions, you can write them into the chat, and we will answer them later in the QA session at the end of this webinar.
Okay. Hello everyone. This is Maged Mokhtar. I'll be presenting the PetaSAN, how to set up PetaSAN services. This is actually a live demo of PetaSAN services. But first, to summarize, we support the common services iSCSI, CIF, SSMB, NFS, and very soon, within days, S3. These services run on top of Ceph. One common feature in PetaSAN that we provide is that, of course, we provide high availability, of course, but we also provide that these services run as a scale-out and active-active fashion. So it's not just high availability mean active-passive, but no, all our services run as scale-out, active-active to make use of better performance, better load balancing, and so on. Okay. Okay, so this here is the first page of PetaSAN. I'll show you how to set up at a high level the service that we talked about. So the first thing is we go to the configuration menu for iSCSI. We'll start first with iSCSI. One thing is that iSCSI uses something common in iSCSI called MPIO, which stands for multipath I/O. Basically, MPIO requires you to have two different networks. So the setup in PetaSAN is quite straightforward. We need to set up both of these networks. In PetaSAN, we call them iSCSI 1 and iSCSI 2 for these two MPIO networks. We are required to specify the interface, the network interface for both networks. So in this example, we'll be using two different interfaces, Ethernet 2 and Ethernet 3, for example. This is a recommendation to use distinct physical interfaces. We do have some users that would put both of these networks on the same physical interface. In that case, they would most probably segregate them with like some kind of VLAN tagging or so on. But the recommendation really in the iSCSI industry is to use physically different interfaces, primarily because of performance and as well as for better availability, so that you have two physically distinct paths for your two MPIO paths. So we set up these interfaces. There's another thing that we set up in PetaSAN, and this is an auto IP range that we have support in PetaSAN. This allows you, makes it much easier when you later on, as we will see, when you create iSCSI disks, you can, instead of specifying the IPs, the individual IPs for the individual disks yourself, you can throw this job off to the system and let the system automatically assign or allocate IPs from the range that we configure here in this page. This makes it much easier. This is very similar to, for example, DHCP. You can of course specify IPs manually via a static IPs. However, it's much easier to have a DHCP server or like a pool of IPs that are available, and that let the system as needed take from this pool free IPs to allocate them. So in this case, we will put a pool of IPs. This is just an example. So a range of 10 IPs from 100 to 110. We will also do the same for the second network, the second MPIO network. Okay. Also, these IPs are what the clients use when they connect to the iSCSI disks. These IPs are not fixed to a particular node. They are again, they're as mentioned before, they're highly available. They can move from node to node. If there's a node failure, they get moved to other nodes. Also, we support moving the IPs dynamically, even in case of nodes that are running. They don't have to fail, but we can, for load balancing purpose, move IPs from node to node while running for better load distribution. Okay, so we're all set with the settings for iSCSI. Okay, we're done. We go again and do something similar to the CIFS or SMB, same thing. Okay, so we also are required to select the interface that the system will use for that service. In this case, I'm going to use the same interface I've used before for iSCSI or iSCSI 1, just to prove the point that you can use the same interface for multiple services if you want. And then we're going to give it also an IP range. Okay. Okay. There is also some advanced settings that we can do. For example, we support connection with an Active directory, joining an Active Directory, a Windows Active Directory domain. So we specify the Active Directory, the Windows domain administrator password, and so on. And this allows you to allows the system to join an Active Directory for authentication. And by this, we're able to provide both a public as well as secure share. So you use the Windows access control list, the Windows ACL security mechanism to protect your shares. This is actually a quite common setup. For advanced users, they can actually go here. This is also in PetaSAN. A lot of things are very easy, very easy. But however, we open the guts of the system. Anybody who wants to go deep, for example, they can go and open up the details of the configuration for everything like the Samba, the Linux Samba SMB server, the Kerberos settings, authentication. They can do a lot of stuff for advanced users, and these settings are cluster-wide. So once they do any kind of configuration, it's propagated to all nodes running the CIFS service. Okay, but we're not going to do that here. We're just going to have a simple setup. Okay. So this is just very quickly how to set up the CIFS service. Very quickly, we're also going to go to the NFS, also quite similar. So we'll specify another IP range. And we specify the interface to use, for example, here. Now, the IP range that we specify, this is the range of IPs that clients would connect to the system on these IP range if they want to get to access NFS services and resources. So this is the range of IPs that the system would expose for clients to connect to. Internally, the system would take that range and distribute it across the services and across the nodes that are, or the hosts that are running this service. So, for example, if you have like a range of 10 IPs and you have two services, two hosts running the services, you try to distribute the IPs among these two. Lastly, there's just a small technicality also for NFS that we need to specify a pool that is required internally for recovery purposes. I'm not going to go too much there, but of course we try, if you try to compare the different protocols, we try as much as possible to make it look similar, to be consistent across the different protocols, so that the user experience is streamlined. However, internally they're totally different protocols, and sometimes they require unique features. For example, for NFS, we do need to define a pool, a Rados pool, that is used internally by the NFS Ganesha for recovery. So we're all set here. Okay, so now we've configured the three services. In version 2.8, we will be also able to configure S3. Again, it's due very soon. After that, now we have configured the services on a cluster-wide basis. We need to assign the nodes that would run these services. So to do that, we go to the node list, and this here are in my demo where I'm running 3 nodes, and we would go to the roles button. This is what Ammar showed while he was in his presentation. That's very easy to add roles to PetaSAN. So in this case, for node 1, it already has a service. We're going to add 2 more services, iSCSI and CIFS. Okay, so now node 1 is configured to run all 3 services. We'll do the same with node 2. Okay, so it's very easy. So now we are ready for business. Now we have configured the services. We have configured their setup. We have configured which nodes run the services. very easily. And also we can do the reverse. We can go and uncheck services if it's really required. So now we are able to use these services. For example, let's start with iSCSI, and let's create an iSCSI disk. Here, this is the current disk. Of course, it's empty, so we're going to add a new one. It's very, very easy. We just name the disk, for example, data store 1, for example. We specify the size, and pretty much that's it. But just want to show you that what I talked about earlier, that if you want, you can manually put the IPs yourself. You have full control on the IPs that you want to put here, but I'll just opt for the automatic IP, which is like a DHCP thing. And just for fun, I'm going to increase the passes. By default, each iSCSI disk gets two passes on your MPIO, one for each MPIO path. But for fun, I'll just increase the passes to 4. Also, for real production, this also makes a big performance difference because you will be accessing more hosts in a scale-out fashion. So we're ready to create the disk. Again, these paths, the 4 passes, are all highly available and can switch from node to node. These are the okay. It's actually the disk is starting now. If I click on the passes, it shows me that right now the first pass has been assigned to node 2, the second pass to node 1, the third to node 2, and so on. So it actually dynamically assign the passes. Typically, the first passes are assigned very quickly to get the disk up and running, and then the remaining passes are adjusted according to load and so on. So we have an iSCSI disk running right now. We can do also, if we want, we can manually control moving paths between nodes. So if we go to the path assignment, we see, for example, that node 2 got 3 passes. Node 1 got 1. This is basically based on load, and if in a real production environment the loads is equal, they would be more or less equal assignments. In this case, I want to move one of the passes, like the second pass from node 2 and put it into node 1, move it dynamically. So I choose I select the pass and say I want to move it to node 1 and assign. And this is dynamic. It does a dynamic assignment. Typically, when we benchmark and test, for example, VMware, it takes a split second for I/O to freeze for like a split second before resuming back again. So its effect on clients is very, very minimized. So here you can see that it successfully moved it. It was a red, green here. So this is how we move passes around. Now for CIFS, we can look at the 2 nodes that we have. We've set up 2 nodes, node 1 and node 2, running the CIFS service. You can see that the IPs that we specified a range of 10 IPs or 11 IPs, and they have been distributed among the two services. Right now there are no connections, but if there are connections, you can actually see the number of connections. You can actually click on them and see who's connected to what file and so on, and some statistics as well. We're going to create a share. We go to create share or add share. Of course, we don't have any shares now. We say add. It's very, very easy. We put the share name, for example, share 1. We select the CephFS file system. We can also select the layout. The layout is a feature in CephFS that you can have different pools within the same CephFS file system. You can have different pools that are, for example, an SSD fast pool, an HDD backup pool. So you can have different performances based on the layouts, depending on the share, whether you want to put the share on a fast pool or a slow pool and so on. So we can do that here. Here we can do whether it's a public share accessible for everybody, if it's browsable for everybody, or whether we want to put some restrictions like an Active Directory, ACL, and so on. In this case, we'll just create a public share, and that's it. So the share is created. This share is being served by all nodes running the CIF server service, and it's accessing, of course, the CephFS backend storage. So it's a very scalable, scale out way. This is for CIFS. We can do something similar also for the NFS. We can look at the IPs. These are the IPs that we specified, the IP ranges that we specified for NFS. These IPs are distributed to across the two different nodes. We can create an NFS export here. So, for example, export 1. Same thing about we can specify different layouts for different performance and so on. We don't support Active Directory. This is for NFS. This is something new. We will support that in the future. But however, our NFS protocol is NFS version 4. But we do have some kind of limited client restrictions. For example, you can have read writes for clients by subnets, by IP range, and so on. This is quite common for usage of NFS. The adoption of Active Directory is still something that's quite new for NFS. Also, just one thing too about the is that when we specify a range of IPs, either for NFS or CIFS, it's better to have clients. There are two possibilities for client access. Either you can distribute these IPs to your clients in an even way and let your clients connect by IP, or you can let your client connect by a DNS. So you can, for example, specify that your service is called, for example, CIFS service, PetaSAN, CIFS, whatever, and this name would be the name of the service, and the clients would resolve that name using a round-robin DNS. So a DNS that has in a round-robin way would serve the IPs that we specify as to and from, so that it would automatically load balance the IPs. That was it for me as an overview of the services. I hope that I just communicated that how easy it is in PetaSAN. They're very easy, and at the same time, it's very powerful. We provide truly scale out active. So I'll pass back to Starline.
Okay, thank you, Maged, for your presentation.
Thank you.
And now if there are any questions, please write them into the chat. Rainer, Amar, and Maged have access to the chat, and then they can answer as necessary. Any questions to the presentation from Rainer or from Amar or from Maged?
Actually, oh, there is a question. Okay, I will wait.
Okay, there's one question. Is the same data set shareable through the CIFS and NFS protocols?
Well, the pools are shared. They both access the same pool. We recommend that they remain separate as separate directories within the same CephFS pool. It is possible that you can make both of them point to the same share. You can do that. It is not recommended. We don't recommend it, and neither does the Ceph developers recommend it. It hasn't been tested a lot, but theoretically, it is possible that both these protocols point to the same directory within the CephFS. In PetaSAN, the top level directory where you create all the shares reside, it's by default called NFS or CIFS by default, but it's one of the parameters that you can change in the settings. If you want, you can let both protocols point to the same root level directory if you want, but it's not recommended again because it hasn't been tested.
Okay, there's one more question about the recordings and slides from this presentation. If you will be able to get them, yes, we will after the end of the webinar, we will prepare the slides and the recording and send you an email with a link where you can get these.
There is a question for me. How will the expansion to 3 petabytes be possible with 4x for you if you already use 3x? So we're using 9 and we're left with 3 slots for 336 base chassis. When the expansion time comes, you are not restricted to using the same disk capacity within the node. You can use 10, 12, 14, 16. Of course, there is a trick because the higher the capacity of the disk, the more traffic it would get from Ceph because there is a weight for each disk based on its individual capacity. So there will be some work or tuning involved here where you basically go to Ceph and say, I want to reduce the weight of the bigger drives by a factor of 0.8 or 0.9, something like that. So each drive would end up receiving the same amount of data and you would end up with 3 petabytes within 12 chassis.
Okay, there's one question to Rainer. When can we expect end of HDD shortage?
It seems it will take a while because there is so much demand now that by just basically industry would have to increase the capacity, and increasing capacity for hard disk drive manufacturing is not as costly as for semiconductors, but it will be an investment cycle of let's say half a year to 3/4 of a year. So we are expecting that by the end of the year, beginning of next year, earliest.
Thank you. Then one more question. How does CephFS scale for a million of files?
Well, it does scale with millions of files. It's been tested in many installations with millions and millions of files. It also, I mean, the factors that depends on this is whether you are writing a lot of I/O or whether a lot of that is metadata, like creating files, creating directories, locking, having clients lock. So a lot of the metadata is what really puts strain on the file system. However, the I/O doesn't put as much strain. So if you have your environment where you're doing a lot of metadata access, like creating subdirectories, renaming files, and so on, then it does put some strain on your metadata servers, the MDS. And in such case, the recommendation is that you would have a powerful host running the MDS. The MDS is run on the first 3 nodes in PetaSAN, so definitely in this case you would have to have really fast nodes for that. Also, the following questions about CIFS powered by Samba. Yes, of course. CIFS internally, this is the only Linux implementation that provides CIFS in Linux. So of course we use that. We of course have like a kind of umbrella above that, which is console, so that what I showed earlier, that you can actually do some configurations. Whenever you do a configuration cluster-wide, it's propagated via the console service mesh, and it kind of it got all the services in different nodes got configured. All the Samba services got configured based on the single entry in the cluster.
I have one comment on how does Ceph scale for millions of files. There is a very interesting article on Red Hat's website. It's titled "Scaling Ceph to a Billion Objects and Beyond." It was written by Karan Singh. He's one of the Red Hat Ceph veterans, and I highly recommend taking a look at it. There is a very interesting proof of concept that they have done to test that. There is also the deployment by CERN in Europe. It's a research center, and it has one of the biggest Ceph deployments on the planet, basically. And they have documented everything, and they have benchmarked the cluster, documented every single upgrade they have went through, and the hiccups and the tips and tricks. I highly advise that you take a look at the CERN blog, technical blog, for more information.
And they are mainly using Toshiba hard disk drives, by the way.
Yeah, yeah, I know. Well, I don't want to sound like I'm promoting, but the failure rate of the drive is a crucial factor when you want to guarantee the safety of your data. So I said this in the first and in the second episode, and it's something that you should never compromise on. You can compensate, for CPU deficiency, RAM deficiency, but anything. It's just one OSD down is not good for you. Even though that Ceph can auto heal and can recover, avoid using cheap hard drives.
Okay, there's one more question. Do you have recommendations for data migration from an old storage infrastructure into the PetaSAN storage in the range from 1 to 3 petabyte? How long would it take?
It would take as much as your network would be able to sustain throughput. Basically, I'm sorry, Maged, I jumped this question, but also not trying to be to give an elastic response, but it depends on the configuration of the cluster and the throughput of the network, because as we said, it's basically a RAID over network. Network throughput is a very significant factor here, and the IOPS capabilities of your cluster. So the faster the performance of your cluster, the faster your network is, the faster the overall migration would be. Maged can also comment on this.
So the bottleneck could also, the bottleneck could also be at the source, because if the source is surfing the data quite slow, the fast network and the fast destination doesn't help.
Yeah.
Yes, just to add to these answers, it also depends on the block size that you move. For example, if you have large files or large images, they typically get moved quicker because of the throughput than if you had a lot of millions and millions of small files and you are accessing them one file at a time. Typically the latency would be or your IOPS would be a larger factor than your throughput. Another thing about Ceph and PetaSAN is that they are built for a concurrency. So if you do want to migrate data, try to get a tool that does concurrent migration. For example, don't just write one file at a time, but try to get a tool that writes a lot of files simultaneously. Or in case of large files, it kind of it chops the file into several blocks and concurrently write those blocks in the same time. You'll get much better performance.
There is a utility for available on PetaSAN's website. It's called PetaSAN Copy, and I think it might be of use in such scenarios, especially if you're migrating data or copying data from a Windows-based client or from a Windows-based cluster to a PetaSAN cluster. Am I correct, Maged?
Yes, absolutely. This is exactly what it does. For large files, it breaks the files into I think 16 threads and writes 4 megabyte objects, which is the object size of the Ceph RBD. So it's very compatible. So it tries to optimize Windows copying with Ceph. So yes, absolutely.
Yeah, and this tool is available on petasan.org/downloads. The name of the tool is PetaSAN Copy. You can download it and test it on your own, see how it performs in your case.
Okay, there are additional questions about the migration. Any tool for such data transfer to take over all the settings of objects and, for example, NFS version 4 access permissions? Are there any recommendations?
I have no recommendation.
I cannot really myself.
I'm sorry, Maged. I personally don't have any recommendations here.
It's same thing. I would expect that some of the high-end tools would take permissions into account. That's what I expect, but I'm not really sure.
Okay, if there are no more questions, I thank a lot to our 3 experts today. Here you get them again. Rainer Werner Kaese from Toshiba, Maged Mokhtar from PetaSAN, and Mohamed Ammar from Starline. Thank you for your presentations, and thank all the audience for joining this webinar. And till the next time, we will see which topic we will get in for next webinars from Starline. Thank you and bye-bye.